Today I'll talk about mathematical basis of Gaussian mixture models. It is part of my series of lecture on machine learning, and Gaussian mixture models can be used for cluster analysis. Gaussian mixture models are probabilistic models for representing normally distributed subpopulations within an overall population. Since mixture models in general don't require knowing the data labels, it is a kind of unsupervised learning. A hint that a data might follow a mixture model is that the data looks multimodal. This is a univariate situation where a data is looking multimodal, and this is the entire population with three subpopulations, all of which are normally distributed. This is a bivariate situation, and we can have a multivariate situation also. So what are the applications of Gaussian mixture model? Gaussian mixture models can be used for cluster analysis, for density estimation, for feature extraction from speech data, for object tracking of multiple objects at each frame in a video sequence, for image analysis. These are some of the uses of Gaussian mixture models. So there are three parameters of a Gaussian mixture model: weight of each component in a mixture, which is denoted by phi, mean of each component, and variance of each component. So Gaussian mixture model with k components, and each of the k component has a mean mu k and a variance sigma k for univariate case. Similarly, for a multivariate case, we have a mean vector mu k and a covariance matrix with sigma k. So this is a univariate case with sigma, and this is a multivariate case with covariance matrix capital sigma. This I have taken from this source. This is a very useful source, very illustrative. So any machine learning model is typically learned by using maximum likelihood estimation technique, which seeks to maximize the probability or likelihood of observed data given the model parameters. Since in present case, differentiating the log likelihood is not possible, hence we use expectation maximization method. Expectation maximization is an iterative algorithm which guarantees to approach a local maxima or a saddle point. There are two steps in expectation maximization methodology. One is the expectation step, which consists of calculating the expectation of the component assignment for each data xi given the model parameters, and these are for each component. Then a maximization step, which consists of maximizing the expectations calculated in the first step with respect to the model parameters. This step consists of updating the values of the model parameters of each component. So this is the expectation step. Here we calculate a latent variable gamma, and this is nothing but probability of xi belonging to C divided by probability, sum of probability of xi belonging to C1, C2, and so on till Ck. So this is the latent variable. And then in maximization step, we use this latent variable gamma to update the model parameters. These are the model parameters. So for cluster analysis, the probability that a data point X belong to a component Ci or a cluster Ci is calculated using Bayes' theorem. And this is the formula for the probability. This is all for today. Thank you very much.